So the name of this lecture is Don't Make This Hard, because don't make it hard, all right? There are 4 reactions, and I know they're presented in a way which is very confusing. I'm going to start with the first and important one. Well, let's see, there are substitution reactions, and there are 2 kinds, what are called SN2, which is useful, and also SN1, which is a bit chaotic. So the good one is that. And there are also elimination reactions.
Elimination reactions.
There are 2 types. A good one is called E2. And there's also E1, which is also, like SN1, chaotic. So they're not so good. They happen by accident, but not by design. And so we're going to just focus on the smart ones. Now, on this idea of the useful reactions, I said the SN2 reaction is a good reaction. It's a substitution reaction, that's yes. Nucleophilic and it is bimolecular. Bimolecular means simply this, that there are 2 chemical species in the rate determining step. So here's the nature of the reaction. There is an organic molecule which has a halogen, let's say bromine, for example. This is the molecule that we've been talking about, just as a model example, which is 2-bromo-3-methylbutane. In all of these reactions, there is a nucleophile. Now, I've told you a few times, a nucleophile is represented this way. I told you a number of times, and I asked you to remember that nucleophile is a chemical species with a pair of electrons that is available for forming a bond to a carbon. That's what nucleophiles do. They look for a good target carbon that is will be welcoming of the electron pair on the nucleophile. So in the nucleophilic substitution, the 2 electrons of the nucleophile find a good target carbon. A good target carbon is one with a halogen, with a good leaving group. And that happens, it's bimolecular. It's bimolecular because both these chemical species, the blue nucleophile and the black alkyl halide, are in the rate determining step. They bang into each other and the reaction proceeds. And you will probably know by now that the product of this reaction, I'm just going to invert the drawing a little bit for our convenience, that when the nucleophile has come in here, now the nucleophile has replaced the bromine on carbon 2. That's the effective and well-designed SN2 reaction. If you want to make an organic molecule with a nucleophile attached to the carbon framework, and you have an alkyl halide to start with, you're going to do fine. You just choose right nucleophile. The second good reaction is an elimination reaction. In an E2, that is, E2 reaction is a bimolecular elimination reaction. It's elimination because a molecule, HX, is pushed out of an organic molecule. So in this reaction, if we start with a compound like this, and we use a reagent, the reagent, it turns out, will be a base. A base is a chemical species with a pair of electrons that it will use to steal a proton from an organic molecule. That's what bases always are in organic chemistry. Sometimes the base has a negative charge, and often when the base has a negative charge, it's a strong base. For our purposes here, it's like a code that we'll play, a game we'll play. Now, in this case, if the organic molecule that we're starting with has a proton on a carbon that we will call a beta carbon. This language of beta, an alpha and beta set, is this. It proposes that for our purposes, if there is a halogenated carbon, we'll call that carbon an alpha carbon, just because it has a halogen on it, just because it stands out. And any carbon which itself is bonded to an alpha carbon will become a beta carbon. In this molecule, there are two beta carbons, two carbons bonded to the alpha carbon. Now, if the base comes along and says, I'm grabbing that proton from that beta carbon, we indicate that by that curved arrow. If there is a curved arrow, I'll use red because we have red for that. If the pair of electrons moves down here to form a second bond, a pi bond between the alpha and beta carbons, and at the same time, the halogen leaves, if those three curved arrows, the attack of the base on the beta proton, the pair of electrons between beta carbon and proton form a new pi bond between alpha and beta carbons, and alpha carbon loses the bromide, the leaving group, we would say that the effect of this, we would represent the product of the reaction indicated by those three curved arrows is this. It's basically the same framework, but now there's a double bond between the alpha and the beta, and an H plus has been removed from the beta carbon, and a Br minus from the alpha carbon. So the elimination is the elimination of the constituents of HBr from the organic molecule. The result with the organic molecule is that the alkane became an alkene. Simple.